Make sure this is back on. Okay, which one?
The denominator 7 times 7.
Where? Oh, did I? Oh, oops. Yeah, 49 here. Sorry. 49. Thank you.
Not necessarily, no. You were the same way. I just followed just notes from it for the first. You are like a mini minds. You must be of one mind. Concentrate. Haven't you ever watched The Last Samurai? Ricky Tom Cruise. You are many minds, other than you have one mind. Who would have been in the money? I messed up a negative.
How are y'all doing on this? Progress or no?
A and B weren't so bad.
Yeah.
Your C and D were a little bit more.
We're not quite done with this, but I mean, we need to talk about these answers because there's something we need to consider here. But I want to make sure everyone can get to these. I do need to proceed. So I want to see, is there anyone that has a specific question on any of these? Like where any of this came from? Guys? No? Anyone? You got it? Sure. Back there, y'all are good? Ladies, you're okay? Are you just being agreeable? Are you're just agreeing to agree, or you understand? Okay. In this problem, you had to figure out what sine of theta was, right? But you only needed that for one of these, right? This one right here. That's the only one you needed the sine theta for. Because this formula right here, you could have used the one that had just cosines in it. These two formulas have just cosine in it. So we could have almost done everything just with what was given. That's just because it was our first problem. But we're not quite there, right? We need to think about something right now. This formula, sine of theta over 2, we actually get two answers, don't we? And if I give you an angle, and you take half of it, you're saying the y-coordinate, right? You're saying the y-coordinate for that angle. How can it be two different things? And the problem with that formula is that you have one more thing you have to go back and check. You have to figure out where the heck theta over 2 is. See, we know where theta is, right? Theta was in quadrant 2. What does that mean? Theta was between
2 pi and pi.
quadrant 2. Pi over 2 and pi, right? That's quadrant 2. Between pi over 2 and pi, yes? So where would theta over 2 be? So divide this by 2, this by 2, this by 2. Where would theta over 2 live? Pi over 2 and pi over 4. What quadrant is that in? That's your first quadrant. Pi over 4 is there. Pi over 2 is straight up. So theta over 2 is in the first quadrant. You with me? If you're in the first quadrant, what is the sine value in the first quadrant? Positive, which means that your answer is not plus or minus this. It's plus only. The formula is great, but it doesn't, it's not both of these answers. Understand? Okay, so we scrap out that negative. It's just a positive. What about cosine of theta over 2? That's your x-coordinate. And if you're in the first quadrant, your x-coordinate would have to be positive. So we scrap, here it is. That's this one right here. Scrap out the negative on that one. So the two correct answers for these two are positive root 8 over 14, and this one is positive root 16 over 14. And yes, you could reduce these and probably clean those up, but I'm just leaving them like that. You don't have to worry about that with these two, okay? You don't have to worry about two different answers because the formula only spits out one. What would, if I asked you for tangent of theta over 2 right now, what would you do?
Take C over 2.
Take this answer and divide it by this answer, right? You would do this divided by this. So you could put that all into one root. 8 over 14 over 6 over 14, and then flip, and that's it. I don't normally ask for tangent of pi over 2 or theta over 2 on a test, but the book does in the homework. It does some of that. I figure, shoot, if you can get to sine and cosine, then you're good for tangent, right? Because you can always just do a ratio. How are we doing on time? 30 minutes? Okay. See how much more I've got to do. Good. We're doing good. We're doing good. Let's do that secant of theta. No, secant's going to be too easy. Let's do cosecant theta equals -3. And let's say that theta is in quadrant 4. Find sine 2 theta, cosine 2 theta, sine theta over 2, cosine of theta over 2.
Is it always going to ask us to look for 2 theta?
Is it always?
Yeah, like are those always going to be what we're looking for?
In this homework, in this section, yes, because this section is about the double angle formulas and the half angle formulas. That's what this is about. So that's what you're going to primarily see here. All right, where should I start? Start with a triangle, right? Okay. I need to know where this is. Now I know I'm in quadrant 2, right? 4, sorry. I'm in quadrant 4. I'm given that, so that's nice. Draw my triangle. And cosecant is the reciprocal of sine, so that's hypotenuse over opposite. That's sine, opposite over, so this is the reciprocal. This is your hypotenuse over your opposite, right? So where does that negative need to be? On the 1, right? So it should be like 3 here and -1 there, right? So that should give us the appropriate. And then we can solve for that other side. Root 8. Positive, right? Because we are in the 4th quadrant. All right, so I'll just jot this down because I need this information. What's sine theta? And what's cosine theta?
Sine theta is -1 over 3.
-1 over 3.
Root 8 over 3.
root 8 over 3. Good. Okay, so that, we can just build that off of our triangle, right?
Now you can plug them into your formulas.
That's all I need for all 4 of those formulas, right? I just need these 2 things.
Yeah, it's plug and play.
Just plug it in. So let's do them.
I get it.
I believe he's at.
I'm sorry.
All right, 2 sine theta. Is it all right that I'm not writing the formulas down each time? Okay, so I'm doing 2 sine theta cosine theta. And then multiplying across the tops, I get negative 2 root 8 over 9. Yes, that cleans up. I don't care. All right, next one. If I have sine and cosine, I like to use the cosine squared minus sine squared. Only because it's easier for me to remember that formula. Because it's almost a Pythagorean, but with a minus and starting with cosine. But the other 2 are suitable. I'll do the one I like. So I'm going to do cosine squared. So I'm taking root 8 over 3. I'm squaring it minus sine squared. So negative 1/3 squared. So that gives me 8/9 minus 1/9. So 7/9. Yeah. Now theta over 2. Before we do theta over 2, we know that the formula says plus or minus, right? Let's try and resolve the plus or minus now. Let's see if we can do that. So how am I going to do it?
The sine will be the minus and the cosine will be the plus.
How though? How are you getting that information?
Well, the sine is the y value and the cosine is the x value. Yeah,
But that's of theta though. But we're talking about theta over 2. So where does theta over 2 live? So you start with this, right? Start with this and write it down as an inequality. Let's write that down as an inequality. I'll stick it right here. Theta must be between here and here, right? So between 3 pi over 2 and 2 pi, yeah? Now to get theta over 2, divide everything by 2. 3 pi over 4 is theta over 2 less than or equal to pi. So where's 3/4 pi?
So it's like the second
Yeah. This right here means we're between 3 pi over 4 and pi. So we're somewhere in there, aren't we? We're somewhere in the second quadrant. And in the second quadrant, sine is positive, right? Your y coordinate is positive. So we're going to take the positive of this answer, right? And then your cosine is negative, so, right, the x coordinate is negative. So I'm going to only be taking the positive here and the negative here. Agreed? Okay. So this should be square root of, sine is the one that has subtract in it. So 1 minus, and what is it, cosine? So root 8 over 3, all over 2. Ooh, I'm going to clean that up. That looks too ugly there. I get a common denominator. Square root. It's 3 minus root 8. That's not an 8. Root 8 over 3 all over 2. And then I can look at this as 2 over 1 and flip, so I could get square root of 3 minus root 8 over 6. And that's probably about as good as it's going to get. I mean, that's some number, right?
I've seen worse.
Yeah. It's a root with a root in it. Oh well. The only difference between that answer and this answer is that we're going to be putting a negative out in front, right? So we're going to have negative square root. And then here it's going to be plus root 8 over 3 all over 2. And that's negative root. And then when we add and get a common denominator, should be 3 plus root 8 over 6. So we got 3 here, put them together, divide by 2. Yeah. Okay. Any questions? No? All right. I think we've done good. Now it's time to do that thing that involves the calculus, okay? That you'll use in calculus later. Write this without powers on any trig functions. So here's the problem. Cosine squared x. I'm going to use x instead of theta. Let's just switch up the variable just for the fun of it, just because we can. All right, I'd like for us to write this where it's rewritten and there's no powers. We don't have any powers. Okay? Now this first one's easy because the power reducing formula I gave you earlier, I told you we can use it to get rid of powers, right? So I can rewrite this as what? 1 plus cosine 2x over 2. Now, do you agree that this expression right here does not have any powers on the trig functions? So we're done, right? We're done. I'm going to go one additional step, though. And you'll see why this step's valuable in a moment. Is that the same thing? Yeah, all I did was factored out a 2 out of the bottom, which is really like a 1/2 out front. Yes? So that's the same expression? Okay. You could almost look at this as being a formula. This is the power reducing formula, just rewritten with x's instead of thetas. And in my Cal 2 class, I tell them, hey, remember this formula from pre-cal? I'm actually going to use this version of it more than I'm going to use that version of it. So in my Cal 2, I go straight from here to here without this step right here. All right, that was too easy because that was just the formula, right? Okay, let's do this then. Cosine to the 4th x.
Write it down as cosine squared x times cosine squared x and take that formula times itself.
So you want to rewrite this as what?
Cosine squared x
Cosine squared x
times cosine squared x.
times cosine squared x.
Formula got for the previous problem.
Use the formula from the previous problem.
Just times it by itself.
Put it here, and then multiply them? That's crazy. Let's see what happens. So if I rewrite this right here, what's that going to become?
The half
We just wrote that down. Half of 1 plus cosine 2x, right? And then this one also becomes times half, and then 1 plus cosine 2x. Do you all agree we could do that?
Yeah.
I mean, why are you doing that to us, man? That's torture. That's legal though, right? Okay, now you might argue right now that these, like, you no longer have any powers. But I would disagree with you because if I clean this up, this is this times this, right? So it is squared. So if I squared that, I would actually still have some powers, wouldn't I? All right, let's square it. Let's actually square that. Let's multiply this times itself. That means FOIL. Should I show it on the side, or you think you can follow me through it? Let me write it down first, and then you can tell me whether or not you... No, I'm going to write it. It's our first one. Okay, I'm doing 1 plus cosine 2x times 1 plus cosine 2x, right? That's what I'm about to do? Okay, 1 times 1, 1
Cosine 2x.
plus 1 times cosine 2x is cosine 2x. Cosine 2x times 1 is cosine 2x again. What's cosine 2x times cosine 2x? Cosine squared 2x, right? And then I can combine these two to become 1 plus 2 cosine 2x plus cosine squared 2x. Yeah? That's what this is. That's what this is. And I still have the 1/4 out here, right? Okay, so I'm going to write that down. 1 plus 2 cosine 2x plus cosine squared of 2x, like that. This still has a power on a trig function. Does this have a power? No. This? No? Okay. We're getting there. We're not there yet. Now what I'm going to do is I'm going to pass that 1/4 through everything. If I pass the 1/4 through, I will have 1/4 times 1, 1/4, plus 1/4 times 2, 1/2 cosine 2x. 1/4 times that is 1/4 cosine squared of 2x. Yeah? So there's only one term here that's problematic, right? That still has the squared in it, and that's this one right here. Can you get rid of the power on just this one?
Now you can switch the cosine 2x as half 1 plus cos 2x.
Yeah, so I'm looking at this one right here, right? And I'm asking, is there a way to rewrite that so that the power's not there anymore? And to remember what I was trying to get you all to see in that formula a second ago, for cosine squared theta is equal to 1 plus cosine 2 theta all over 2. That was the power reducing formula that I put on the board. And I said, look, what I want you to see is that if you have cosine squared of some junk, that in the new formula it becomes double the junk, right? Twice the junk. So here, if I'm trying to get rid of cosine squared of 2x, it's going to become a 4x in the formula. So this, which is just this part right here, right, is going to become 1/2 1 plus cosine 4x. That's this formula being applied to a 2x and me pulling the half out to begin with. So I'm going to rewrite this again. This is 1/4 plus 1/2 cosine 2x plus 1/4, but then this 1/2 and then 1 plus cosine of 4x. That looks like a mess. So this right here, right, is just this piece right here. Now let's multiply this out. 1/4 times 1/2 is 1/8. That 1/8 can pass through to both of these terms. So I will now have 1/4 plus 1/2 cosine 2x plus 1/8 plus 1/8 cosine 4x. Okay, so that became 1/8, and that went here and here, and that's how I got these two. Yeah, I'm not done. I can put 1/4 plus 1/8 together. That's 3/8. So 3/8 plus 1/2 cosine 2x plus 1/8 cosine of 4x. Done. I now have rewritten that in terms of trig functions that no longer have powers. And you might be asking yourself, why would I ever want to do that, right? Well, it turns out that in Calculus 2, we do something that's called integration. Calculus 1 is about something called differentiation, taking derivatives. And Calculus 2 is about what's called integration, which is the reverse process of taking a derivative. So it's like in Cal 1 you learn how to walk forward, in Cal 2 you learn how to walk backwards.
And then what's Cal 3?
Cal 3 you like break dance and you moonwalk and no. Cal 3 is basically Cal 1 and Cal 2, but in three dimensions or higher. So you go to higher dimensional things.
Higher dimension of thinking.
So instead of curves like on a flat sheet of paper, you're looking at like surfaces in three-dimensional space. And then you can include vectors in there and vector fields. So you have some object moving through some path in three-dimensional space that's being acted upon by some electromagnetic force. You can compute the amount of work it requires to go through that. I mean, it's Cal 1 and 2 in higher dimensions. That's it. You have a z coordinate, yes. And then you can go past 3 dimensions. You can go up to really any dimension. In Cal 3, we stop at like 4 or 5. Fourth dimensional. It's weird. Okay, was this okay? I mean, it's only the second example you've seen, so you should see one more. All right. How about this? Now, I will admit something to you before I begin this. This is somewhat, it's in that gray area between trying to illustrate what we're doing and torture. It's a little bit in between. Like, this is going to hurt a little bit when we do this. But it's more than a fair problem in Cal 2. Like, the length of the work I'm going to do here is more than fair play. Or it's within the realm of sanity in Cal 2. Like, okay, yeah, we can do that. That's not a big deal. But it is a little bit torturous, like a little bit of torture. It's like monotonous. All right, so we need to do what we just did a second ago. We need to try and reduce this power out. We did last time cosine squared times cosine squared, right? So I could do here sine squared, sine squared, sine squared.
And then we take the whole class.
And then, okay, so let's see. I'm going to do it like this. I'm going to do, yeah, let's do it. Sine squared x times sine squared x times sine squared x. Each one of those has its own reduction, right? So this first one turns into 1/2 and then parentheses what? 1 minus cosine 2x. And the next one does the same thing. 1/2, 1 minus cosine 2x. And the next one, 1/2, and then 1 minus cosine 2x. Oh, this looks lovely, doesn't it? Let's get all the halves out front. 1/2 times 1/2 times 1/2 is 1/8. And then I have 1 minus cosine 2x times 1 minus cosine 2x, not squared x, sorry, 2x. And then 1 minus cosine of 2x. So that's cubed. That's that times itself, 3 times. Oh, man. Most people are okay with this. If I give you like x plus y and ask you to square it, most people at this level are okay with the idea that there's kind of a general formula for that. It's like you square that, you put at the ends, you multiply these two together and you double it. Have you all gotten to a point where you're that like comfortable with that? What if I put a minus in here?
Then it's just negative out of the negative 2x.
Yeah, you got this and then minus 2xy plus y squared. So the only difference between these two is that you would double it. I mean, sorry, that it's negative here. You missed, it was awesome. It's okay, but I mean, yeah. It's all. All right, so, but is there one for cubed?
I mean, there is.
There's got to be one for cubed, right? Yeah. I think I'm going to offer this because I don't feel like finishing it right now. I don't think we have enough time to finish this. I don't think we have enough time. I'm going to offer this as a bonus to be turned in next class. Now, here's the catch to it. There's a little catch. If you wind up with an expression that has a trig function that's to an odd power, that's okay. But if it's an even power, it must be power reduced. So see how we started with sine to the sixth? I don't want you to have anything left that has anything to an even power. So if you wind up with like a sine cubed, fine. Okay, you can leave that one alone. It just can't be sine squared or cosine squared or sine to the fourth or cosine to the fourth. Understand? The reason is in Cal 2, we can handle odd powers. When we're trying to do that backwards moonwalking, well, no, moonwalk's Cal 3. When we're trying to walk backwards in Cal 2, odd powers are easy to do, even powers are harder. So we have to do the power reducing on the even. All right, does that seem like a good little bonus? I would maybe turn your paper sideways and write that way to keep, this is going to really open up and it's going to be a lot of work. Now, I still have 6 minutes and instead of working this out, I wanted to actually talk about that because I think that's worth talking about. Okay, what is x plus y to the first power? X plus y. I'm going to do it like this. If you've seen this before, please don't spoil it for everyone else. X plus y squared is x squared plus 2xy plus y squared. Okay, x plus y cubed is x cubed plus 3x squared y squared 3yx y squared y cubed y. Okay, so that's what it is. All right. What about to the fourth power?
No. Never gone that big.
X to the fourth plus
4x.
4x cubed y.
3x.
6x, come on, you should have known it was 6. 4xy cubed plus y to the fourth, right? All right. I'll go all day. You want me to go? I'll keep going. I'll go all day long. I can do that. X to the fifth plus 5x to the fourth y plus 10x to the third y squared plus another 10x squared y cubed plus 5x y to the fourth plus y to the fifth. So I'm now showing off, right? I'm a badass up here. You want me to keep going?
Yeah.
I can keep going. I can tell you right now, I can just go all day long.
Where's the pattern at?
There's a pattern. Obviously, I'm not that smart, okay? There's a pattern.
It's like the x reduces, the y increases.
Yeah. Notice that about every single row here as we move across. Let's start with this one because I think it's easier to see with the powers here. We start with the power 5 here, right? So we start with an x term to the fifth power, and there is no y term. The number in front is a 1. We move to the next one. Forget the number for now. What's the power? 4. So the x power went down, and now the y appears. Next one, the power in x comes down. Now the y power went up. Next one, the x power goes down again. The y power comes up. Next one, same thing until you get to the end. At the end, now the y is to the fifth and the x is gone. At each one, you could say that power is added to 5. But the pattern is more like down with the x's and up with the y's, right? Same thing happens here, same thing happens here. So help me fill in the next part.
How do we
I'll get the numbers in a second, yeah. So the next one would be x to the sixth, right? Plus, there would be some number in front, x to the fifth, y, plus some number, x to the fourth y squared plus some number
X3, Y3,
x to the third y cubed.
X2,
Keep
Y,
going, plus x squared y to the fourth plus xy to the fifth. One more,
Y6.
some number y to the sixth. Now I said if you've seen this before, don't spoil it. Has anyone seen where we get these numbers from? No?
Heidi, like this is some binomial thing.
Yes, it has to do with the binomial theorem, yes.
That's all I know.
Let's look at these numbers. Okay. Oh, there's one I left out. Sorry. We never talked about x plus y to the 0. What's anything to the 0? 1. Okay. Now, what I'm going to do is I'm going to come through here in red, and I'm just going to highlight all the numbers. 1, all the coefficients for everything I see. Okay, 1, 5, and I can keep going, right? Now what I'm going to do is next to this, I'm going to write those out again, but without all the variables there, without all the x's and y's. I had a 1, and then I had 1, 1, then 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Yes, 1, 6, 15, 20, 15, 6, 1. Okay. Here's the rule. The ends are always 1. Okay? Now, the number of numbers you have is like, so we have one number here, right? And that was the 0th power. In the first power, we have 2 numbers. In the second power, we have 3 numbers. In the third power, we have 4 numbers, right? Fourth power, we have 5. The way you get the numbers is if the ends are always the ends are always 1s, this number comes from the sum of the 2 above it. So this row here, I have 1 and 1. How do I get this number? 2 and 1. 2 and 1 give me 3. Here are 1s. How do I get this number? 4, 1 and 3 here. 3 and 3 is 6. 3 and 1. Understand?
Professor, I mean, if someone asks us like, what's x plus y to the power of 47? So like, do we know what's x plus power of 46 and then come to 46?
Okay, so your question is, me presenting this way, well, let's get one more row, and then I'll answer your question. What would my numbers be here? Well, I always start with the 1. I always end with the 1, right? Now, this number is going to come from the sum of these 2 numbers. So 6. This number is going to come from the sum of these 2 numbers, 15, then 20, then 10 and 5 is 15, and then 5 and 1 is 6, and then a 1 at the end. So that's why I was saying I could go all day. You see, I could go all day now because the next one I start at x to the 7th, and then I just follow. Once I have the first established, I can just keep going. Your question is, I think this is your question, what is x plus y to the 47th power?
Yeah.
Can you do it without having to develop the entire grid out, like the entire table? By the way, this is called Pascal's triangle. The answer is yes, but we have to use a formula to calculate these coefficients. There is a formula. It's called the binomial formula to calculate these coefficients. And so you would need to know, 47, you would need to know the power that you were at, so like what position you're in. So the short answer is yes, there is a way to do it without having to create the whole table. It's called Pascal's triangle, named after a mathematician, but not the mathematician who found it. The Chinese found this long before Pascal found it, but he gets the credit. All right, we got to go. So try your homework on this. That's your bonus question. 8-6, that bonus question I gave you. You can do that if you want. You don't have to. Sine to the 6th power. Write it out. You can have odd powers, but no even powers.
And is this extra credit to what?
I'll do it on a test. I'll add 5 points.
We're always going to have a bonus on the test, right?
Just have a bonus.
Now, would it be for a lowest test or a highest?
It doesn't matter. They're all weighted the same, so it won't make a difference.